Find the volume of the region above the xy plane, bounded between the sphere of radius 4, centered at the origin, and the cone z squared equals x squared plus y squared. First, we're going to get an idea of what our picture looks like. So I draw in my sphere, radius 4, centered at the origin, and then our cone, z squared equals x squared plus y squared, is just going to be a cone facing up. And then we notice they're going to intersect at this circle here, and then what we have looks like an ice cream cone. Suppose we integrate in cylindrical coordinates. So we're looking for r, theta, and z that defines our region. If you notice, I have a top function, bottom function, so we're going to look for z first. Top function is the sphere, so x squared plus y squared is going to be r squared in cylindrical. Push it to the other side, take the square root. So we'll have z equal to plus minus square root of 16 minus r squared. Since z is always positive, we're going to throw away the negative solution. So that's my top function. Then take x squared plus y squared equals r squared, z equals plus minus r, and again we throw away the negative solution. That gives me my bottom function, r. Once I integrate in z, that projects everything down to the xy plane. So I want to find coordinates that define this disk. Now it's going to do one loop, so theta is going to go from 0 to 2 pi. So I just need to find the radius. Now, radius, how can I get that? Well, take a look at both of our equations and see if we can solve for something when they intersect. So we're looking for this circle here, which is just going to go straight down to the xy plane. Okay, well, if we put z squared in for x squared plus y squared, I'm going to get 2z squared equals 16, or z equals square root of 8. Then I could put that into, okay, we know r squared plus z squared is equal to 16 in this case. So that's going to mean we'll have r squared plus 8 equals 16, r equals square root of 8. Okay, another way to get this, we know the angle here, okay, for our cone is going to be 45 degrees. So if I know the z, which is square root of 8, then the radius coming out this way is also going to be square root of 8. So that just checks our work. So we have our limits. Theta goes 0 to 2 pi, r goes 0 to square root of 8, z goes from r to square root of 16 minus r squared. Now we can integrate. Now, we need to change our differential, dx, dy, dz, in rectangular to the differentials in cylindrical. So dx, dy goes to r, dr, d theta, and then the dz stays as it is. So what we're going to integrate, okay, I'll do dz first, then dr, and then d theta. Okay, d theta can go anywhere, but I have to have dr being integrated after dz. The reason for that is, if I look at z, we have r in the limits, and the idea is going to be when I integrate a variable, it's supposed to eliminate it from the integration. So if I did r first, I'm not going to be able to integrate it because these limits will be sticking around if z is in the second spot. So we do it as so. So this is just following your nose now. All right, so we first integrate with respect to z. There's no z in here, so dz just goes to z itself. We evaluate, take the difference, gives us this term here. Multiply by the r, so that becomes an r squared. If I integrate with respect to r, that's going to go to 1/3 r cubed. And then we got to worry about this mess here. Okay, well fortunately we have the r there, so I can do a substitution. So we'll have u equal to 16 minus r squared, and then we could just work that out. That's going to turn into 1/3 16 minus r squared to the 3/2. So work over here. Now, we put in our square root of 8, put in our 0, take the difference. That gives us this thing here, which is slightly messy. You'll note, okay, 16 to the 3/2, square root of 16 is 4, cubing that gives me a 64. That's where I get my 64/3. Then if I take 8, cube, and square root, well, you'll note, okay, that's a square root of 8 cubed, so that's square root of 8 times itself 3 times, so that's going to be 8 square root of 8. Take 2 of those, I get 16 square root of 8, so that's how I get this term here. And then everything's over a 3. So, only thing left, integrate against theta. Okay, there's nothing in theta here, so we're just going to send d theta to theta, evaluate, take the difference, gives me a 2 pi out in front. So that is our volume. Let's check our work by integrating in spherical coordinates. So here, the limits are going to be easier to find, but the price we'll pay is you may have to work to get your differentials. So let's take a look at the picture. Spherical, we're looking for rho, theta, and phi. So theta is going to be the same as it was in cylindrical. Rho is going to be the distance from the origin to your point. And then phi is going to be measuring the angle for the positive z-axis. Okay, take your point, take the plane, measure down to your point and that plane. So phi is going to be between 0 and then pi if you go all the way back down to the negative z-axis. So let's take a look at our picture. Okay, we have the snow cone. So if you notice, for rho, okay, we're going to basically get every point between the origin and this piece of our sphere. So there's going to be nothing getting in the way. So at least on this region we're interested in, rho is going to range from 0 to 4. For theta, again, same idea. We're just going to do one loop around. So that's going to give me 0 to 2 pi. Only thing we need to worry about is phi. Now, one thing you can do is, if you eyeball it, you'll notice we start at 0, which is the positive z-axis. We're going to come down to the 45-degree line. So in phi, we start at 0. We stop when we get to pi over 4. All right, if you want that really tight, what you do is, okay, we can take a look at what's happening in the xz plane. So we're looking at what's happening with the cone. If we take the trace in the xz plane, so that's setting y equals 0 in the equation for the cone, that gives me z equals x squared, or z equals plus minus x. So we're looking at these two lines here, and if I'm looking at z equal to x, then that's going to be a line at 45-degree angle. Okay, if it's 45 degrees below, 45 degrees up top, so we're looking at going down to pi fourths. So those are all the limits. To integrate, we need the spherical differentials. So how do we change dx, dy, dz? It's going to go to rho squared sine phi, d rho, d theta, d phi. Okay, probably best to memorize this, but if you absolutely have to rederive it, here's how you go. So we draw ourselves a little spherical cube. Now how you get that? You're going to start at the origin. Okay, you're going to have a little change in rho out here. Okay, we'll call the entire thing rho. What are you going to do? You're going to have a little change in theta. That's going to be this top piece here. And then a little change in phi, which is going to give you this little height here. All right, first let's take a look at the side view. So what we're going to have is, we're going to have our change in phi. I'm going to have d rho along the bottom, rho being the long side. And then I just want to get the area of this. So we're going to treat it as a rectangle, even though it isn't. What happens is it gives us the correct answer for the differential that we integrate against. So what are we going to have? Our base is just this little piece, so that's going to be d rho. So I just want the height. So what's the height going to be? Well, I want the length of this arc here. So what's that? That's going to be your angle times your radius. Radius is rho. My angle is going to be d phi. So the area of this spherical rectangle is going to be d rho, rho d phi. Now, to get my volume element, we just need the width. So the width is going to be this little length along the back. We take a look at the top view. We're trying to get this piece right here. So let's first go to the side view. Go to the side view again. What I'm looking for is this length, okay, projecting down, looking from the top in the XY plane. So I'm looking for this leg of this right triangle. Okay, our angle coming down from the positive z-axis, that's going to be phi. So if I take rho, which is the hypotenuse, times sine of phi, that's going to give me the opposite. Okay, and the opposite is just going to be the same as the leg that we're looking for. So this leg is rho sine of phi. Now, the picture moves. This leg goes from here to right here. If I want the width, which is along the back, it's that arc of the circle, what am I going to do? It's going to be angle times radius. We just found the radius. That's going to be rho sine of phi. Okay, our angle is just going to be our little change in theta, which I'm calling d theta. So if I find radius times angle, that's going to be rho sine phi d theta, and that's my width. Take the width times the area here, and then you'll notice when you reassemble everything, you're going to get the differential up here. Okay, that seems like a lot of work, but better to memorize. For all that work to get the differential, the integral is a straight shot. So if we put our element of integration in, what's going to happen? You notice all the limits are going to be numbers, so there's no dependence among our variables when we integrate. So that's going to mean you can actually separate this thing into 3 separate integrals, okay, each of a single variable. So for instance, if I want to do the theta, okay, there's nothing in here that's going to get in the way, okay, or with the limits. So I could just do integral, theta goes from 0 to 2 pi of d theta, gives me a 2 pi. Do it in phi, so phi goes from 0 to pi fourths, sine phi d phi. Any derivative of sine is minus cosine. Put your pi fourths and your 0 in, take the difference, and clean the signs up, you get a 1 minus square root of 2 over 2. And then for the rho stuff, we're going from 0 to 4, rho squared d rho. Add 1, flip it over, we get 1/3 rho cubed. Put 4 and 0 in, take the difference, you get 64 over 3. So here's your volume. Now, let's show that it agrees with cylindrical. So we distribute the 64 over 3 to the inside. What's going to happen? The 64 over 3 looks familiar. Then we're going to have the 2 in the bottom cancels against the 64 to give us a 32. I pull a 2 off of that 32, gives me a 16. If I push 2 into a square root of 2, that goes in as a 4, which gives me a square root of 8. And then you notice this agrees with the answer for cylindrical.